20 all the way around past 16 to 16 again. Let's see. Okay. And then 0. Let's try it again. Maybe it was 16, 20, 0. Let's try that. 16 and all the way past 20 and 20 and then 0. I bet that was it. Okay, maybe it was 0 and then 20 and then 16. I can never remember my combination. I just get so angry between classes. I try to open up my combination lock and I just can't. I need to learn something about combinations before I can do this. Let's see what today's lesson has to say about combinations.
Alright, today we're going to talk about combinations as outlined in our intro. And the thing you need to remember about combinations is that for some arrangements, the order is important. For example, when we have a zip code, 75243, the order matters because 25734 is a completely different zip code with the same 5 numbers. And so what we need to make the distinction between is permutations and combinations. Because for other combinations, like a $10 bill, a $5 bill, and a $1 bill, the order doesn't matter. You still have $16. This is a combination. Okay? Order does not matter for a combination. Okay? So in reality, it shouldn't be called a combination lock. It should be called a permutation lock. Because in combinations, the order makes no difference. The order is simply saying, how many ways could I pick them when it doesn't matter what order I pick them in. Okay? And so when we look at choosing letters, so for example, we have 3 letters from the set A, B, C, D, E. If we look at A, D, and E, we could have different possibilities. So we have A, D, E, but we could also have A, E, D. We could have E, A, D, or E, D, A, or we could have D, A, E, or D, E, A. 1, 2, 3, 4, 5, 6 distinct possibilities. So really what we're saying is, in a combination, the order doesn't matter. Okay? So we have 6 permutations for 3 letters. Also, that would be 3 factorial. We've discussed this before. There are 3 factorial different ways to arrange those letters. Well, really, so what we're doing, we're assuming order does not matter. The math of it looks like this. We have the permutation of 5 objects chosen 3 at a time. Because we have 5 letters, we are picking 3 of them. And we're going to divide by the number of repeat orders. So 3 factorial, that's for the repeat orders. So the math of it looks like this. It's 5 factorial over 5 minus 3 factorial. That's the permutation part. And also on the bottom we have 3 factorial. So it looks like this. 5 factorial over 3 factorial, 2 factorial. Okay? So that gives us 5 times 4 times 3 factorial over 3 factorial, 2 factorial. When I cancel out a couple of things here, the 3 factorial and this, I end up with 20 over 2, which is 10 ways. There's 10 ways to pick 3 letters from 5 total letters and arrange them in distinct ways. Okay? So it doesn't really matter. There's 10 ways to pick those 3 letters. okay, when order doesn't matter. Well, that would be assuming that all of these ways represent the same three letters being picked. Okay? And so combinations in general look like this. We have the permutation of n objects chosen k at a time, and we're going to divide by the factorial of the number of things that we have chosen. Okay? So the math of it looks like this. N factorial over k factorial times n minus k factorial. K is the number of objects chosen. Okay? So that's the math for a combination. So let's look at a couple of examples. A common example when we start to talk about statistics is playing cards. And so if we have a 52 card deck, we are going to pick from 52 5 of them. Okay? So that would be the number of 5 card hands. But what we need to take into consideration is the fact that if we have 5 cards, we could arrange them in any order. And so we are going to actually be doing the combination of 52 things. Let me rewrite that. That was a little sloppy. 52 things, chosen 5 at a time, right, is equal to, really, this. Okay? So that would be equal to 52 factorial over 5 factorial times 52 minus 5 factorial. Let me bring it down here for a second. 52 times 51 times 50 times 49 times 48 times 47 factorial over 5 factorial, and then this is going to be 47 factorial. I'll cross out things on the top and the bottom that are the same. We end up with 2,598,960. That's over 2 million hands. That's almost 2.6 million different combinations of 5 cards. Now you see why poker is so lucrative, because you can bet on a hand, but there's 2 million, almost 2.6 million other hands that it could possibly be. Okay? So that's how this works. The combination formula is slightly different because the variations, we're dividing by the number of objects that we're picking. Okay? Here's another example. Let's consider a basketball team. And for a moment, we're not ranking them or putting them in any specific positions, so we have 11 players. And we want to choose 5 of them. Well, we're going to choose from 11 5 of those players. Well, what this gives us is 11 factorial over 5 factorial, 11 minus 5 factorial. It's a simple formula that we're plugging into. So we have 11 times 10 times 9 times 8 times 7 times 6 factorial over 5 factorial, 6 factorial. We cancel out. So we end up with 462 ways to pick 5 players from 11 players on the bench, considering the fact that there are not distinct positions, meaning order does not matter. So for combinations, order does not matter. Okay? The next example I'm going to give you to do. Go ahead and write it down and bring it to class tomorrow. We will discuss it. It's a lot like the previous example, so make sure you took notes on that one. Okay? I'm going to go on to another one. This one's about cards. Oh, sorry, about committees. So, a committee of 5 is chosen from 5 mathematicians and 6 economists. So what we have here is kind of like a problem that we've discussed before. There's 2 separate pickings that we're doing. We are choosing 3 economists and 2 mathematicians. Well, really, here's what we're choosing. We have 5 mathematicians. And we only need to choose 2 of them, right? Because here we have the 2 mathematicians on our committee. We're going to multiply that by the combinations of picking from 6 economists, 3 of them. Okay? Because remember, this is a lot like that problem we did the other day, where we have 5 total slots to choose. Okay? And it's 2 distinct ones. So to pick these, it's combination of 5, chosen 2 at a time, and over here it's the combination of 6, and we're only choosing 3 of them. Well, we're going to multiply them together to get all of the possibilities. So the math of it looks like this. We'll have 5 factorial over 2 factorial, 3 factorial, times 6 factorial over 6 over 3 factorial and 3 factorial. Okay? And what we end up with is a total of 200 ways to pick this committee of 5 from 5 mathematicians and 6 economists. Okay? That's the other type of problem that we can do where we have 2 distinct groups that we're choosing a select number from. Here's an example for you about the IRS. It's coming up on tax season, so this will be an appropriate example for you to do. Remember, you're dividing it into 2 separate problems. So try this one and bring it to class. You may have to pause here to write this one down. Okay? Think about it. He's using 3 corporate and 2 individual from out of 4 and out of 6. So think about that. Last example that I'm going to do before you have one to do. This one's about cards. From a standard deck of cards, which is 52 cards, 5 are chosen. How many 5-card combinations contain 2 kings and 3 queens? When we're talking about 5-card combinations, really what we're talking about is the total number of objects that we have to choose from. Okay? So, let's think about this. If we are choosing from the number of kings, there's only 4 kings per deck. And there's 4 queens per deck. And so what we're choosing is, out of 4, we're choosing 2 of them. Okay? And we're going to multiply that by the combination of, out of 4, choosing 3 queens. The 52-card deck is really arbitrary in this case, just to say that there's only 4 total in the whole deck of kings. And so when we look at the math of this, it's going to be 4 factorial over 2 factorial, 2 factorial, times, because once again this is 2 separate sections because there's 2 queens, or 3 queens and 2 kings. And this is going to be 4 factorial, and then 3 factorial, 1 factorial. When we do this math, we end up with a total of 24 ways to get just the kings or the queens. Remember, that is 24 out of a total of 2.6 million possible 5-card hands. Let's think about the possibility for getting 5 hearts. How many of each suit are there? Well, if we take 52 and we divide it by 4 suits, we get 13 cards per suit. Okay? Remember this number because this is going to come back. So if we are choosing just from the hearts, we are choosing out of 13 cards because there's 13 possible hearts. We are choosing 5 of them. Okay? So when we do the math, we get 13 factorial over 5 factorial and 8 factorial. We end up with 1,287 ways to choose just 5 hearts. It's mind-boggling how many ways there are to choose just 5 hearts. So think about what that means for getting like a royal flush, which is the 10, Jack, Queen, King of one suit. That's 1 out of these 1,287 ways. It's crazy. Okay? So 5 cards of the same suit would be based on the same combination that we had up here. We are choosing from 13, 5 of them, just like the 5 hearts. But instead, we are going to multiply it by 4 total suits. Because we're not saying we just have to have hearts, we're saying it's hearts or spades or clubs or diamonds. So there's 4 total suits. So this is going to be 1,287 times 4, which gives us 5,148 ways. Okay? That's basically how this works. The last example is one for you to do, so I'm going to pause on it for just a second. You are choosing 5 of them. You want to see how many would contain 4 of the same suit. Alright guys, so you're doing 3 examples for me. This one and the other two, the one about the IRS and the one about the softball team, bring those to class tomorrow. Thanks for watching, guys. We'll see you next time.